So without delaying further, we have our first speaker, Ryan Mans, who will talk about spectral theory and geometry.
Yeah. Oh.
You need to switch the screen back.
Yeah. Yeah, okay, so like you mentioned, I'm going to talk briefly about spectral theory and geometry. My mentor was Professor Antoine Proof, who cannot be here today because he's in France, so yeah. Okay, so the outline is I'm going to talk about the Laplacian for a bit and the eigenvalue problem, and then show some examples in the geometric cases of S1 and the torus T2, and then related to Thales' law in both cases. So as you guys probably know, the Laplacian is the composition of the divergence and the gradient, and it's just a C infinity function in our case because we don't want to care about Sobolev spaces, and if the resulting function is also differentiable. So the nice property is that it's invariant under translation and rotation, and the goal is to kind of treat this like a matrix over a vector space and diagonalize it. So specifically with the vector case of L2, because it's a Hilbert space and it's got a nice inner product, and this, we can use the spectral theorem and some other nice tools to uncover some facts about its spectrum. Okay, so I'll just jump into the case of S1. This is the actual Helmholtz equation, which is the eigenvalue problem, which is probably familiar from linear algebra. So in the case of S1, which is just R mod Z, all of our functions are one periodic. And we're just going to assume, again, we're in some sort of a Sobolev space, so our output function is also in L2 of S1. And writing out the ODE is very simple. It's just a single variable. So we solve the characteristic equation. We look at some cases of lambda. Clearly, lambda can't be negative because in this case, we have real exponentials, which are very much not one periodic nor periodic at all. So we restrict ourselves to the case of lambda being positive. And in this case, what's up? In order for it to be one periodic, lambda must be some 4 pi squared k squared for an integer k. And so we get these solutions to the eigenvalue problem. And so our eigenfunctions are given, or the eigenspace is the span of these two complex exponentials. It's pretty intuitive. And yeah, here's the spectrum. For any k, which is integer, it's the 4 pi squared k squared. And so, yeah, what we've effectively done is decompose this periodic function on the basis of complex exponentials, which, as you probably know, is the Fourier series, which you can take for any periodic function in L2. And to generalize this a bit further, just with a circle of arbitrary length L, or R mod LZ, we just do a simple reparameterization. I'm not going to show the details, but you just replace x with Lx, and you go through the calculations again. Your spectrum is now 4 pi squared k squared over L squared, and the eigenfunctions also have a division of L in the exponent. So yeah, pretty simple, pretty interesting, I guess. What's really interesting is Weyls' law. So Weyls' law is essentially asking the question of how do these eigenvalues distribute themselves in whatever space they live in. And specifically, it's interesting in the case where your spectrum is discrete. Or if it's continuous, it's not that interesting of a question. So we look at this eigenvalue counting function, which is essentially just like a PDF of the eigenvalues. And it includes the multiplicity, I should add, which is important because each multiplicity of these eigenvalues is 2. 0 has multiplicity 1, trivially. And so, yeah, for the L-length circle, we get that the asymptotic bound of this counting function is the square root of the eigenvalue times the length divided by pi. And then we generalize this as some constant, the eigenvalue to the power of dimension over 2, and then times the volume, or just the length of the circle. Yeah. And so this is really interesting because it's an inverse problem in a sense. So if you think of the musical instrument, like a triangle, and you turn it into a circle and you hit it. So just from hearing the spectrum of the circle, we can discern some geometric facts about it, like specifically its length. And this is kind of boring in one dimension, but it's cooler in one dimension. Like you can effectively hear the shape of a drum. If you have a drum, some type of manifold, a square drum or a circle, and you hit it and you listen to its spectrum, you can discern its area and the number of holes and some other facts, and we'll get into that later. And yeah, the proof is quite simple. You literally just take some eigenvalue mu and you fix the counting function. You get this k bounded by the floor of this guy. What's up? We know every eigenvalue has multiplicity 2 except for 0, which is 1, so we just express it as this. And of course, The asymptotic is mu to the 1/2 times L over pi, and the generalization was this. So, yeah. Okay, now on to some more interesting stuff, which is extending to the case of the torus. This is a two-dimensional case, but I'm not very good at PDEs, so it's quite simple to analyze because it's just the product of the two previous cases. So it's just S1 times S1, and so what we essentially do is we curry the previous case, we freeze one of the variables, we do our Fourier decomposition, and then we do it again on the frozen variable. And yeah, I won't go through much of these details, but yeah, you do the single variable Fourier transform. Your constants here are a function of the frozen variable x2. You plug this guy into the eigenvalue problem. You discover that your variables, or your constants of a function of c or x2, also satisfy the Helmholtz equation in one dimension. And so, yeah, your spectrum is essentially the norm of some 4 pi, or some n squared and the k squared of the first function. So, okay, I said that really bad. I'll skip over some points. All these CKs, these constant functions, are also in L2, which is important. And yeah, these mu's, so they also satisfy this Helmholtz equation, and these guys are also in the spectrum. So your solutions look like this. You have your k and your n for k and n and z. And so you can just express your spectrum as a function over z2 instead of z1 now, and specifically the norm squared of some z. And yeah, so now you can express your eigenfunctions as an inner product of your m and z2, your lattice point, and your input x. And actually, the multiplicity now is quite complicated. I'll get into it in a second, but it's no longer just multiplicity 2 or multiplicity 4 or some like intuitive jump. It's any any lattice point that shares the same norm squared. So yeah, we'll get into this in a second. But I plotted we made a calculator to plot some of the eigenfunctions on the torus and project it into R2. And we like made some sliders so you can slide the coefficients around and plot some cool functions. I don't know, they're interesting, and it looks cool, so that was pretty fun. But like I mentioned, there's no closed form solution or formula for the multiplicity of these eigenvalues. So this is known as the Gauss circle problem. You're probably familiar with it. Our counting function is now just like the number of lattice points in this circle of radius mu, or the circle of radius eigenvalue that you're looking at. So in this case, if we choose a norm of 3, norm squared is 9, we get a multiplicity of 4. It's just the intersection of the circle with the lattice points. And the counting function is all the lattice points within there. So relying a bit more on heuristics here, the area of the circle you can approximate as the number of lattice points inside. You've probably seen this before. For small radius, it's quite a coarse approximation. But as you send mu off into infinity, this well approximates the area of the circle. So we can approximate the counting function by just the area given by the circle of radius mu, and this becomes mu over 4 pi, or more generally, some constant times mu times the volume of the torus. And some other calculations that we did were estimating this remainder. So the conjecture is that there's some additional term of big O times, or of mu to the 1/4 plus some epsilon. And so here you can see that the blue is the actual remainder term up to the eigenvalue of 10,000. And the red line is the conjecture, the actual bound for epsilon equals 0.06. And then here we're kind of estimating the value of epsilon for different radii. So this is pretty interesting as well. This was done earlier in the semester. Yeah. So, okay. We then looked at the distorted torus, and there's different, ways to interpret what we mean by distorted torus. In this case, we're just applying the diffeomorphism to the lattice. So it's actually the same topologically, because this A is a deck transformation, so it's got the same fundamental group and same topological properties and all that. But we're defining this new lattice, like I said, using this matrix, any invertible matrix. And then we define its respective dual lattice as well. It's giving explicit by A inverse transposed times the original lattice C2. And now we're looking at functions instead of R2 mod Z2, but we're now looking at R2 mod AZ2. And similar to the case of SL, where we just did a reparameterization, we set y equal to Lx, where L was the length of the circle. Now we just set y equal to AX, where A was our diffeomorphism from before. And we get that the spectrum is now the same as before. Yeah, same as here. But now we're looking at m's in the dual lattice instead of just Z2. And again, our eigenfunctions are also with respect to this dual lattice. So same form of the eigenfunctions, but any m with the same norm as this m in the dual lattice. So what this kind of looks like is so we look at Vela's law now, we approximate the circle area by these like distorted lattices, these distorted squares. Trivially, the volume of the manifold is now determinant of A, because you're just looking at the area of this unit square, and you kind of tile the plane with that. And so, yeah, Vela's law now becomes just some constant times your eigenvalue times the determinant of A. So again, just to rehash this, the significance is that given just the spectrum of the Laplacian on your manifold, you can discern the volume of the manifold, or in this case, the volume of the distorted manifold, and hence the determinant of A, which created the distorted manifold just from the spectrum. And we can add modifications to this, like the number of holes in the manifold, pretty easily using either like a deformation retraction and looking at like an equivalent manifold, or kind of just like with heuristics. But we did do that, but we didn't include it in the presentation. So yeah, that's kind of all I have. We also looked a lot at the Poisson summation formula, which is quite interesting in the case of spectral theory, and also we looked quite a bit at some deck transformations and some topological facts in spectral theory. But yeah, I didn't want to include those in the presentation just for brevity. So yeah, thank you.
Any questions for Ryan?
You go a couple slides back.
Yeah.
Yeah, actually this slide. I just wanted to make sure on that second bullet point that that's meant to be an A inverse on Z2, or like is it A inverse transpose, or is it A
Where?
On that second bullet point, you say that capital lambda star is equal to A.
Yeah, this is just poor notation for A inverse transpose.
Okay.
Yeah.
That's what okay.
Yeah.
What's on abelian lambda Z?
Yeah, just maps lambda to Z over abelian.
Okay.
Yeah. Any other questions?
Is there a reason you always have negative in your...
It's just convention, yeah. If you don't have the negative, then your eigenvalues are negative. So then this is all going backwards, and it makes Vela's law just reverse. Like you're just looking at negative eigenvalues instead. And then you're...
So it's still conjecture now?
This is the conjecture. The remainder term is the conjecture, yeah.
I see.
Actually, this should probably be like strict equivalence. We're looking for the exact remainder.
Do you mensural on this?
Sorry, that? What?
Do you mensural on this, like this problem?
I don't think he works explicitly on this problem now. I'm not really sure what field would focus on this problem, other than just an analyst, I guess. Yeah, seems like an analysis problem to me. Yeah. Any other questions?
I guess you're working in all of L2, which the Fourier transform famously is like not super nice in L2, right? It's usually nice in L1. So are you just like omitting the fact that we're acting on Schwartz functions, like we're doing the distributional Fourier transform? And
Yeah.
want to talk about that, or is he just brushing under the rug?
No. It's actually not so important in this case.
Isn't it kind of like a torus, like there's no Schwartz function?
Yeah, Taurus, I guess, is nice.
Yeah.
But are we only? I guess I might not remember. I thought are we not using L2 of all of R, or are we just using it in the Taurus? Oh, just
L2 of the whatever.
Never mind.
Yeah.
You're good. You're good.
So it's pretty obvious.
It's a big deal in the Poisson summation formula. You do only use it with test functions. You restrict to test functions, and in that case, there is. Which really, I should have talked more about the Poisson summation formula, but there's a distributional version as well. I'm not sure if you're familiar with the Poisson summation formula, but You can express it as like the sum over the integers of a function is equal to the sum over the integers of its Fourier transform. But you can also give it in a distributional sense, like the sum over delta functions over the integers is equal to the sum of like negative Gaussian functions. In that case, yeah, you're only restricting to test functions, but I think in this general geometric case, we can take any function in L2 of the domain.
Yeah, because you're in the torus. So
Yeah. Cool. Okay.
Any more questions?
Thank you
If
guys.
not, let's thank Ryan once again.